There we go. And let's go ahead and share the screen. Okay, so hopefully you can all see this. Let me know if you can't. You should be seeing the slides for today. And so, yeah, so our goals for today are relatively ambitious, but I think reasonable, manageable. I want to sort of start with the big goals from today and then work backwards. And so I'm going to go ahead and, yeah, make this full screen. Okay, so we've got some big goals for today. The biggest of these goals is to prove the mean value theorem. So the mean value theorem is one of those big theorems from calculus. You might remember it from Calc 1, or at least remember that there was something called the mean value theorem. And what the mean value theorem does is it says that if there is a function f that's continuous and differentiable on a closed interval from a to b, then there exists a point somewhere in the middle, so there exists some c value in between a and b that satisfies f prime of c equals f of b minus f of a over b minus a. And there's a lot of geometry sort of hidden in that equation, right? So the picture that we want to have in the back of our heads that's related to the mean value theorem is this one. So we take some axes, we take 2 points, call them A and B. And let's say we have a corresponding height f of A and a corresponding height here, f of B. Right, then the idea is that no matter what our function actually looks like maybe it sort of looks like this, who knows, no matter what our function looks like, we could draw a straight line from one point to the next. I'll choose a more contrasting color here. We could draw the straight line from one point to the next. And that line would have a slope of f of b minus f of a over b minus a. Right, so the slope of that line is the sort of change in height. That's the f of b minus f of a over b minus, that's the change in height divided by the change in x values, and that's b minus a. So that's the slope of that line. And what the mean value theorem is telling us is that there is some point in the middle, call it c, right? So maybe that's our c value. There's some point c for which f prime of c, the slope of the tangent line, drew that poorly, I'll do it again. The slope of the tangent line should be equal to that quantity, the f of b minus f of a over b minus a. So there's our point c, and f prime of c is representing the slope of the second line. And basically these two lines should actually be parallel to each other. So the mean value theorem is saying that somewhere in the middle, we can also say this in terms of rates of change, somewhere in the middle there's a point where the instantaneous rate of change, right? That's what's happening right at the point C. The instantaneous rate of change is equal to the average rate of change across the entire interval from A to B. So we can formulate it in terms of slopes of tangent lines. We can formulate it in terms of average versus instantaneous rates of change. And we can sort of see what's happening here in this picture. We can formulate it algebraically as well using this algebraic equation. So the mean value theorem is maybe hugely important in the theory of, of calculus, right? The mean value theorem turned out to be one of the fundamental tools in proving the fundamental theorem of calculus. So the mean value theorem is huge. Our ultimate goal today will be to prove the mean value theorem, sort of starting at the bottom and working our way up. And so sort of looking down the line a little bit. So we've got next on this list is Rolle's theorem. Rolle's theorem is sort of the baby case of the mean value theorem. So it's the easier case. So it says that if our function f is continuous and differentiable, and if we have a point, if it's defined on a and b, and if f of a is equal to f of b, right? So those two heights are actually the same, then there is a point somewhere in the middle for which f prime of c is equal to 0. we realized that Rolle's theorem is just the mean value theorem in the particular case where f of a is equal to f of b. Notice if it's equal, if f of a is equal to f of b, then f of b minus f of a, that numerator becomes 0, and this equation just simplifies down to say f prime of c equals 0. So everything, I should say, Rolle's theorem is the particular case of the mean value theorem where the two endpoints start off at the same height. The corresponding picture is going to be done like this, right? So when we have from A to B, we have that average rate of change will just be flat, right? The average rate of change will be 0. And then there's some point C, let's say in the middle, where f prime of c, we pretend that's a nice straight line, the instantaneous rate of change there is 0. So we can pretty readily use Rolle's theorem to prove the mean value theorem. Before we get there, we'll have to prove the extreme value theorem, right? So we can use Rolle's to prove the mean value theorem. To get there, we'll have to use the extreme value theorem to prove Rolle's theorem. And the extreme value theorem was another one that is important enough to have a name and that we discussed in Calc 1. The extreme value theorem says that if a function is defined on a closed and bounded interval a to b, and it's continuous, then it achieves its absolute maximum value and absolute minimum value, right? Those are going to be sort of the tallest and the lowest points on the graph. And those are the extremes of the function, is where the name comes from. That'll be the extremes of the function. Okay, so we'll need the extreme value theorem to prove Rolle's theorem. And then finally, we will need this theorem, maybe not quite fancy enough to have its own name, but theorem 11.4 in the text to prove the extreme value theorem. And now that's going sort of working backwards, that's getting back to the language that we've discussed recently. So if f is a continuous function and we have a subset of the domain, call it capital A, then we have this statement. If A is compact, then f of A is compact. In other words, a continuous function sends a compact set to its image, and then the image will also be a compact set. So A will send compact sets to compact sets. All right, so a lot of our goal for today, sort of like our biggest goal for today, is actually to prove 11.4. And then we will discuss strategies in which we can use 11.4 to prove the EVT, use the EVT to prove Rolle's theorem, and if we have enough time, we can use Rolle's theorem to prove the mean value theorem. So that's going to be sort of our game plan for today. Okay, and so we need to talk about this theorem 11.4. 11.4 said that if we have a, what was it? It was a continuous function, and then the idea was if A is compact, then f of A is compact. So we have to review what we mean when we say that a function is compact. Okay, so we have the following sort of sets of definitions. Some of these will be the same as what we've already seen, right? And then one of them, this last one, is going to be brand new. So first, we have our original definition of what it meant for a set to be compact. We said that S is compact if and only if every open cover of S contains a finite subcover. So that was our original definition, our very, very challenging definition of what it means for a set to be compact. After a lot of work by all of you, we were able to consolidate several results back in chapter 8 to get this theorem, the Heine-Borel theorem, which gave us a nice way to characterize compact sets. So the Heine-Borel theorem said that a set is compact if and only if it is closed and bounded. Right? So we went from this really challenging definition involving open covers and finite subcovers to this: a set is compact if and only if it is closed and bounded. Now, that's going to be the definition. Well, I'll say that will be the theorem that we use to talk about compactness today. So won't be talking as much about open covers and finite subcovers. Instead, we will be talking about sets that are closed and bounded. But we need to use this next definition or this related definition about something called sequential compactness. All right, so a set is said to be sequentially compact if every sequence in the set has a subsequence that converges to a point in the set. So if every sequence B sub n has a subsequence B sub n sub k that converges to a point in the set. All right, so let's think through exactly what that means first of all, because I think that's a little goofy. So I'm going to draw a real number line here, and I'm going to define my set S. I'll just sort of draw like a picture of it, right? So maybe my set S contains like several different pieces. Everything in pink is my set S. So a set is said to be a set is said to be sequentially compact if every time I take a sequence in it, right? So here I can construct my sequence in S, right? Maybe this is B sub 1, B sub 2, maybe B sub 3 jumps up here, B sub 4 jumps back, maybe this is B sub 5, and so on, right? I can create a sequence of infinitely many points in the set. But as I continue, the idea then is that this is going to have a subsequence that converges to a point in the set. So in sort of an extreme example, let me erase a lot of those. In an extreme example, let's say that I'm creating my sequence B sub n so that B sub 1 is all the way over here, maybe B sub 2 is all the way over here, B sub 3, B sub 4, B sub 5, right? And so on and so on. I create this sequence in which every odd B, so B sub n with n odd, is over in this piece of S, and all my other ones, maybe where my B's are even, are going to occur somewhere over here, B sub n where n is even. Well, clearly, the sequence B by itself does not converge to anything, right? It's going to just keep bouncing back and forth and back and forth and back and forth, right? So it'll keep ping-ponging around, and that overall sequence won't converge to anything. But if my set is sequentially compact, I'm guaranteed that I can find some subsequence, right? Maybe I just take all of these odds, or maybe I even take a smaller set, like a selection of the odds, and I find some subsequence that's just marching up and marching up and marching up and converging to some point B that is in the set itself. Right? So that is what it means for a set to be sequentially compact, that every time I choose a sequence, B sub n, I can find a subsequence that converges. And you'll notice this has a similar feel to the original definition of compactness, right? The original definition of compactness up here said, if you take any open cover, you can find some subset of it, some finite subset that continues to cover S. Down here, we're saying you take any sequence that exists in the set, and I can find some subset, some subsequence that converges to a point in the set. So that's this new definition, this new idea of sequential compactness. Any questions about this new definition for sequential compactness? Any questions at the moment? All right. I'll take your silence to mean you're doing okay for the moment. Let's see. So erasing this for a second. So it will turn out that sequential compactness is equivalent to compactness. And that's what we're going to prove next. So we will actually prove that compactness and sequential compactness are two sides of the same coin, right? Or they're two sort of equivalent definitions. And this is going to be great because every time I know that a set is compact, I will automatically know that it's sequentially compact. And going back to our big goals for today, right? This theorem down here, it turns out that if we're looking at a compact set A and we're trying to show that its image is also compact, it turns out that it's easier to work with sequential compactness than it is to work with regular compactness. And so our goal then will be, well, maybe I'll say, so once we show that compactness and sequential compactness are the same, we will use those ideas, compactness and sequential compactness, to address theorem 11.4. So let's try to show that these two ideas are actually the same, compactness and sequential compactness. And we are, like I said, we're using this Heine-Borel version of compactness. So we're thinking of, we're thinking of a set S being compact if and only if it is closed and bounded. So we're thinking of it like that. So let's see. So this is an if and only if statement. We'll have to prove both directions. Let's try to say that if our set is compact, then it is sequentially compact. So in the forward direction, we can say, let S be compact, meaning that it's closed and bounded. Okay, so we need to show that it's sequentially compact. In other words, we need to show that every sequence B sub n has a subsequence that converges to a point in the set itself. So we have to show that a statement holds true about every sequence that lives in S. We can say let S be compact, i.e. let it be closed and bounded, and let B sub n be a sequence in S. We can let B sub n be a sequence in S. So we're picking this arbitrary but fixed sequence, and our goal is to show that it has a subsequence that converges to a point. Now, how can we go about doing that? Let's find out. We need to recall some old, I guess, not definitions. We have to recall some old results that we have. So if our set is compact, it is closed and bounded. And since it is bounded, right, so we'll start there. Since it is bounded, choose a better color. Since it is bounded, that means that our sequence is bounded, right? Since S is bounded, we know that our sequence B sub n is bounded, and therefore, we know that, now this is a result that we'll have to try to remember. We know that therefore B sub n has some convergent subsequence. All right. Now, why is that true? Or what was the result there that said that was true? Since B sub n is, since S is bounded, B sub n is bounded. And because B sub n is bounded, there is some subsequence, which we could call, let's call it B sub n sub k, that itself converges. Right? Where did that result come from? Anybody remember?
Was it in chapter 5?
Yeah, it was. I think so. I paused in part to give you a chance to think and also grab my copy of the text so I could look up exactly where it is. It's definitely in chapter 5. It has to do with subsequences. And it had to do with, yes, it had to do with ultimately proving the sort of relationship between subsequences and convergent sequences and Cauchy sequences. But the big result that we ended up using, or that we need to use here, was something called the Bolzano-Weierstrass theorem for sequences, basically saying every bounded sequence has a convergent subsequence. And so that's true. So I said, therefore, right? That's this Bolzano-Weierstrass theorem. It's really theorem 515. I'm sorry, 513 from way back in the text. So we've used the fact that S is bounded to extract a convergent subsequence. So B sub n, or rather the subsequence, so B sub n sub k converges to a point B. And B is a real number, right? Of course, because we're working in the real numbers. So B is a real number. But what we don't yet know is we don't yet know whether or not B is actually an element of S. Right? So we know that there's a subsequence that converges to a point in R. We don't actually know yet that it is in S. And so here's where we'll need to use the fact that S is closed. So B sub n sub k converges to a point B in R. B will actually be an accumulation point, right? An accumulation point of the set, or of the set S. Because if it's a limit of a sequence in S, then it's going to be an accumulation point of the set S itself. So B will be an accumulation point of S, and since S is closed, right, it contains its accumulation points, including the point B. So in fact, we have proven that our sequence B sub n has a convergent subsequence, and that convergent subsequence converges to a point that is in the set itself. And so we've fully proven the forward direction. In other words, if a set is compact, then it's definitely sequentially compact. All right, so we're going to transition in a moment to go in the reverse direction. Any questions about that at the moment?
Yes.
Yes.
How do we know that B is an accumulation point?
Oh, how do we know that B is an accumulation point of the set?
That's because it could.
Thank you for asking. And that is a detail that is not, I sort of just said here, it would be an accumulation point, but I didn't really justify that. So I do appreciate you asking that. So that's going to be an old result. If you give me a moment, I'll look up exactly where it is. I think it was probably in our chapter on sequences. So that's probably chapter 4 somewhere. And I can also, if I can't find it right off the top, or in a, if I can't find it in 30 seconds or less, I can sort of do a more hand-wavy proof by picture.
Okay, no problem.
Yeah. Okay, so it's going to be, I think this is the result that we want to look at. It's lemma 4.28. Lemma 4.28 says that if we have a sequence in a set S and it converges to a limit L, then either L is in S or it's an accumulation point of S. So I guess what I should have said here, right, by lemma 4.28, either B is an element of S or B is an accumulation point of S, right? B is an AP of S. Okay, and if it is in S, then we're good to go, because that's what we were trying to show to begin with. And if it's an accumulation point of S, then since S is closed, it turns in S anyway. So no matter what, we'll get that B is an element of S.
Thank you.
Well,
yes, that makes sense. Thank you.
Cool. Awesome. 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 Yeah, thank you for asking. Great question. Okay, let's go ahead and look in the reverse direction here. So now we have to show that if it is sequentially compact, then it is compact. In other words, we want to show if S is compact, if S is sequentially compact, then S is compact, which for us means S is closed and bounded. Right, so we want to show those two things. If S is compact, we want to show it is closed and bounded. And we'll do that in 2 steps, or like 2 separate proofs. We'll show first, if it's sequentially compact, then it's closed. And second, we'll show that if it's sequentially compact, then it's bounded. And so for the first half, we're trying to show, for the first half, we were trying to show that it's closed. And I'm going to construct a slightly heuristic argument, but one that we could make really explicitly rigorous. In short, we're going to prove the contrapositive. In fact, we'll prove the contrapositive for both of these. So suppose S is not closed. Right, so if S is not closed, then there exists an accumulation point of S that is not in the set S itself. So there exists a point, there exists a point P that is in S, in S prime, that is an accumulation point of S, but not in S. All right, so there exists this point, it's an accumulation point of S, but it's not in S. And then our idea is that we're going to construct a sequence in S that converges to S, that converges to P. All right, so in a heuristic picture, right, our set S doesn't have to look like this at all. But if I have my real number line and I have my set S, and let's pretend that S sort of looks like this, but has an open side to it, or something like that, right? So S is not closed. So it has at least one point that is an accumulation point, but is not actually in the set itself. So that can be our point P here, an accumulation point of S that is not in S. Then what I'll do is I'll construct a sequence that is in the set S and converges to P. So maybe this is B sub 1, this is B sub 2, this is B sub 3, and 4, 5, and so on. And these will get closer and closer and closer to P without actually touching P. And so this sequence will converge to P, despite living entirely in S. And I can construct such a sequence because P is an accumulation point of the set. This is actually, we just referenced lemma 4.28 in our previous statement. This is lemma 4.29. Lemma 4.29 says that we can construct a sequence in a set that converges to an accumulation point of the set. So we can construct a sequence in S that converges to P, And because it converges to P, since it converges to P, every single subsequence will also converge to P. Right, so since B sub n converges to P, all subsequences of B sub n also converge to P. And we can conclude then that there does not exist a subsequence that converges to a point of S, because every subsequence converges to this point, and that point is not in S. So we can say that S is not sequentially compact. Okay, so I think we've shown, or at least we've attempted to show, that first half. Any questions about that?
What theorem did you say that was by?
Oh, 4.29, lemma 4.29. And that was for this idea, right? So this idea here, to construct this sequence.
Is that what you used for, since it converges to P, then all subsequences converge to P?
Yeah, that's something else. Thank you, Jesse. So 4.29 said I could construct a sequence that converged to P, and then the result that I was just quoting involved subsequences, right? So if a sequence converges to P, then any possible subsequence I choose also converges to P. And that would be a chapter 5 result. That would be theorem 5.10. So we had
okay.
that was right here, 5.10.
Perfect. Thank you.
Yeah, no problem. I'm going to take this moment. I hate looking at myself and seeing that I'm basically like half in shadow, like a Sith Lord or something. So I'm trying to adjust myself to make myself visible on the screen. Hopefully that's a little better. Okay. Yeah, so slightly hand wavy, but I think we can find those results, 4.29 and then 5.10, to really help us out here. Love it. Yeah, great questions. Any other questions? All right. So let's do the final step of this. I'll erase this. And the final step is to show that second statement, right? So if our set is sequentially compact, then it is bounded. And again, we're actually going to do this by contradiction. Actually, it'll be very, 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 or I should say by contrapositive. It'll be very similar to the proof we just put up. So by contrapositive, suppose S is not bounded. Right? Well, what does it mean for a set to not be bounded? It means that I cannot find a number n that is bigger than all of the elements in the set. Right? So for every n, there exists some element of the set, there exists an x in S that is, or that satisfies absolute value of x is bigger than n. Right? Otherwise, if I could find such an n value, or rather, if I could not find such an n value, then there would be some giant n that was bigger than all of the x's, and that would be a bound on my set S. So for all capital N, there exists some x value that's bigger than n. And we're going to use that idea to construct our sequence, which will break the idea of sequential compactness. So for all n, there exists this x. let's go ahead and give that x value a name. Let's call it B sub capital N. Right? So I'm constructing a sequence, you know, B sub 1, B sub 2, B sub 3, etc., such that B sub n is an element of S and it's bigger than its index in absolute value. So we know then that B sub 1, B sub 2, B sub 3, dot, 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 as a sequence, that's a subset of S. And we know that B sub 1 is bigger than 1, B sub 2 is bigger than 2, etc. And because we've defined our B sub n this way, we know that not only does B sub n diverge, it sort of goes up to infinity, or at least in absolute value, it goes up to infinity. Not only does it diverge, but there is no possible subsequence that could converge, right? So this sequence and every possible subsequence diverges. Right, B sub n and all possible B sub n sub k's all diverge. And because of that, we have found a sequence in S that does not have a subsequence converging to a point in S. In fact, we have a sequence without any subsequences that converge at all. So S is not sequentially compact. Right? And it turns out to be a very, like we said, a very similar argument to the last one. We just took what it meant to not be bounded and used that to construct a sequence that broke the definition of sequential compactness, or that was a counterexample to the definition of sequential compactness. Okay, we'll pause there. So I think if we're happy with this, then we have found a, then we have essentially proven the theorem in both directions. Thumbs up. Okay, so this is great. So now we actually have three completely different ways to describe compactness. We have the original definition, right, the open cover definition. We have the closed and bounded definition that was due to Heine-Borel. And now we have this sequential compactness definition. And so we can now see how we can use these different definitions when appropriate, right? We can sort of choose which one best fits our needs for a given proof. And so we will see that in action right away as we look at theorem 11.4. So now we begin sort of our big sweep of results that happen in chapter 11. So theorem 11.4 says that if f is a continuous function and A is a compact subset of the domain, then the image of A will also be compact, right? This is sometimes said in a really nice way. I really like this, that continuous functions send compact sets to compact sets, or continuous functions preserve compactness. It's a way that we can describe, or characterize a continuous function, is that it preserves this mapping or this idea of compactness, sending compact sets to compact sets. So, how can we go about proving such a thing? Well, let's turn to sequential compactness, and let's turn to some of our results from earlier in the semester, right? Again, we're sort of finding great results from earlier in the semester to help us out here. So if we want to try to prove this, let's see what we can do. Let's say let f be continuous. Let A be compact. And what I mean by that, of course, is that it's compact and it's a subset of the domain. So let A be compact. and a subset of the domain. Okay, we want to show that f of a, the image of A is compact. And to do that, we will show that the image of A is sequentially compact. Right? Because we just finished showing that if it's sequentially compact, it will also be compact. So want to show f of A is sequentially compact. To do that, we need to show that it satisfies the definition of sequential compactness. And we'll do that by taking an arbitrary sequence in the set in question. In this case, the set in question is the set f of A. We'll take an arbitrary sequence, and we will show that that sequence has a subsequence that converges to a point in the set. All right, that's going to be our strategy here. So to do that, we'll say, I guess, yeah, to this end, let's take B sub n to be a sequence in f of A. Right, a sequence, oops, in f of A, or that's a subset of f of A. Okay, I'm going to pull up a picture, not pull up a picture. I'm going to draw a crude picture or a rudimentary picture, right? Here's my function f. Here we go. Here's my function f. It's mapping real numbers into real numbers. And specifically, it's mapping a set A, which is some compact set over here in the domain. So that's my set A, right? Maybe it's not connected. Maybe it has like two pieces. But I have my set A in the domain. It's closed and bounded. And my function f is mapping it to some set over here, right? This is the image of A. And I'm just going to, we don't know what it looks like, but I'm going to draw it kind of like that. So we have f of A, the image of A over there. To show that f of A is sequentially compact, I'm going to take this arbitrary sequence, right? These are the B's. Right, so maybe again, this was B1, this is B2, this is B3, but I have this sequence that's existing over here in f of A. I have this sequence. My goal is to show that there exists a subsequence that converges. Now to do this, I'm going to do the following. For my B, let's say B sub 1, I'm going to recognize that if B sub 1 is in my image, it must have gotten mapped to from somewhere over here, right? At least one spot. Maybe it got mapped to, maybe there were 2 points that mapped to B sub 1. Maybe there is this point that mapped to B sub 1 and also this point. So there might be multiple points that map to B sub 1. I'm going to pick one of those points, right? So maybe doesn't really matter without loss of generality. Let's pick this one. And let's name that A sub 1. So A sub 1 is a point. So there you go. A sub 1 is a point in the original domain A, and it satisfied the fact that f of A sub 1 is equal to B sub 1. Does that make sense? So I'm going to take the pre-image of each of my points, my B sub i's or my B sub n's, and identify at least one point over in the domain that came from there. So maybe this is A sub 2, and it mapped to B2. Maybe this point is A sub 3, and it mapped to B sub 3. and so on and so on. So in a natural way, we will construct a sequence A sub n that's in A such that f of A sub n equals B sub n. Okay, how do we feel about that, right? I sort of did the sort of argument by picture. It was sort of a proof by picture, but does everybody believe that from this sequence, this B sub n sequence, I can construct this corresponding A sub n sequence? Yes, love it. Okay, great. So now things are getting exciting because we have a sequence in A, and we know something about A. We know that A is compact, right? And actually, this is a fun time to point out. I actually have not used either of the assumptions in the proof, right? I haven't used the fact that F is continuous, nor have I used the fact that A is compact in this argument yet. So now we get to use the fact that A is compact. Since A is compact, it is sequentially compact. And so every sequence in A, including A sub n, has a subsequence that converges to a point in A, right? So we can say, since A is sequentially compact, A sub n has a subsequence A sub n sub k that converges to a point, call it A, and A is an element of the set A itself, right? This word here is supposed to read converges. So this set, or this sequence, this subsequence converges to an element of A. So maybe it's not every single point of A. Maybe it's, say, this one, that one, right? Maybe it's only a handful of these, but we can pull out this subsequence and it converges to some point, maybe I'll star it, some point A that is an element of capital A. And now we're going to do the very natural thing. We are going to consider that subsequence and consider the corresponding subsequence over here, right? So maybe it's the, some subsequence over here, and we're going to ask what happens to that subsequence. So we can consider the corresponding B sub n sub k, which was equal to, right? Maybe I'll put this in parentheses. This is equal to f of A sub n sub k. What does this converge to? Or what happens here? Well, now we get to use the one fact that we haven't used yet. We get to use the fact that f is continuous, because we know something about continuous functions and how they interact with sequences defined in the domain, and then the corresponding sequence defined in the codomain. And I believe this was called something along the lines of the sequential criterion for continuity. So I'm going to look it up. This would have been in chapter 6. This would have been in the main body of chapter 6. Yes, and we've got the sequential criterion for continuity. This is theorem 616. And it says that if our function is continuous, that's equivalent to saying that any sequence converging to P over here, right? Or rather, I should say any sequence A sub n converging to A over here must have the corresponding sequence F of A sub n converging to f of a in the codomain. So by the sequential criterion for continuity, let me try that again. By the sequential criterion for continuity, which is just theorem 6.16, the b sub n sub k's, because they are f of a sub n sub k's, the b sub n sub k will converge to f of a. And since A was an element of capital A, this object, right, the f of A will be an element of f of capital A. So f of A, which is an element of the image of A. And we've actually done it. We have shown that if we have an arbitrary, or if we start with an arbitrary sequence in the set f of A, then we can extract a subsequence, b sub n sub k, that converges to an element of f of A. And so we have shown that f of A is sequentially compact, and therefore that f of A is compact. Make that a big one, because we're very proud of that. Ooh. All right, any giant tombstone, because we killed it, yeah. Yes, okay. Any questions about that? Any concerns at the moment? Okay, great. So let's keep going. I'm trying to keep one eye on the time here, and I think we are in a good place to get most of these big results, because now they start to fall a little more like dominoes. So because we now know that a continuous function will map a compact set to a compact set, we can get the extreme value theorem basically for free. As a reminder, the extreme value theorem said that f achieves an absolute maximum and an absolute minimum if f is a continuous function defined on a closed and bounded domain. Right, so our function, if it's defined from a to b, let's say, again, who knows, maybe it looks like this. But if it's continuous, then it will absolutely have an absolute minimum, right? That could be the minimum value. And it will have a maximum value, possibly at the endpoints, but that's okay. Possibly in the interior, and that's also okay. But we will definitely have a maximum and a minimum value. If we don't include the endpoints, of course, all bets are off, right? Because if we didn't include the endpoints, we could have some sort of vertical asymptote. But if we have a closed and bounded domain, we must include those endpoints. And if our function is continuous, then it must achieve these extreme values. So actually, this proof is really, really quick and relatively easy given what we've just accomplished, as long as we recognize it as such. Right? So the proof of the extreme value theorem is if we have f is continuous, right? So since f is continuous, and since the interval, since the interval a to b is compact, right? A closed and bounded interval is a compact set. One of our groups proved that last week. So since f is continuous and since the interval from a to b is compact, we know that the expression f of a to b, the image of the function, is also compact. Furthermore, since the image is compact, that means it's closed and bounded. Since it's bounded, it has a least upper bound and a greatest lower bound. And since it's closed, those two elements, the least upper bound and the greatest lower bound, are in the set itself. right? So let's see if we can spell that out. Since the image of A to B is also compact, therefore or thus f of A to B is closed and bounded. Since it's bounded, the greatest lower bound and the least upper bound exist. And since the set is closed, both the greatest lower bound and the least upper bound are in the image itself. So they are elements of that image. And that's exactly what we were trying to show, right? These are therefore the maximum value and the minimum value because they're the greatest lower bound and the least upper bound. So to see that in an image, right, if the set from A to B was our first compact set, then f of A to B, right, the image is all of this region here in the codomain, right? So that is f of A to B. It is itself a compact set, so it is closed and bounded. And because it's closed and bounded, it has a least upper bound, that's right there, and a greatest lower bound, that's right there. And because the set is closed, they must be elements of the image itself. So they will be the maximum value and the minimum value of the set. Cool. And so we see how this, this more complicated theorem, Theorem 11.4, actually gives us the extreme value theorem, the one whose name we know, basically for free, right, when we realize that these kind of sets are just compact sets. Any questions about that? All right. Cool. Well, rolling right along. Yeah, let's see what else we can do. So this brings us to Rolle's theorem. Rolle's theorem is, again, sort of the simpler version of the extreme of the mean value theorem. And it's the one that says that if our function is not only continuous on the interval from A to B, but actually differentiable on the interval A to B, then there is some point in the middle for which f prime of c will equal 0. All right, so it turns out that the key here is going to be to use the extreme value theorem in a clever way. So proof. Let's say, let f be continuous on the interval A to B. Then, by the extreme value theorem, f achieves a maximum height, right? And that maximum height maybe occurs, maybe that's f max, and a minimum height. Maybe that's f min. Okay. And so the argument that we want to make is that one of these two, at least one of these two, will occur somewhere in the middle of the picture, and that will be a point where the derivative is equal to 0. Again, I'm gonna draw the exact same picture basically that we had on the previous slide. From A to B, imagine I have something, I don't actually quite remember what it looked like. Let's pretend it looks something like this. Right? And what we said was that this height down here, that was the minimum height, that was f min, And this height up here, that was F max. So the drawing that I have, I think, is actually not completely valid because we need this additional assumption. We need f of a to equal f of b. So we need them to be at the same height. So let me redraw this. At the moment, notice f of a and f of b are at wildly different heights. So if I wanted to redraw this, maybe it looks like this. Right? Maybe my function looks something like that. So the idea then is that I have these two different heights, f maximum and f minimum, but one of them is going to have to occur somewhere in the middle of the interval, right? Somewhere between a and b. The way that I've drawn this, f max is occurring at the endpoints, but f min is occurring in the middle. It cannot be the case that both f max and f min occur at each of the endpoints because the two endpoints are the same height. If they didn't, or rather if f max and f min were both equal to f of a and f of b, then our function would just be the horizontal line, right? The flat line. So we can say that because we're not in the, or rather I should say, if our line is flat, if our function is a constant function, then every point in the middle satisfies f prime of c equals 0. So we can say, maybe that's sort of like a case. If f max equals f min, the function is constant. Right? Otherwise, we can construct, well, I shouldn't say we can construct. Otherwise, if f max is not equal to f min, at least one of the two, right? So either f max or f min is not an endpoint. Without loss of generality, let's assume it's the minimum value, right? So let's assume it's the way it is in the picture, and let's assume it happens at some point in the middle. Call that point C. So without loss of generality, let f min occur somewhere in the middle. Cool, and we can say it like that. So at some point in between A and B. Now the argument that we want to make is that f prime of c must equal 0, right? So we want to show f prime of c must equal 0. And to do this, well, I guess from the picture, it seems pretty clear that's our end goal, and at least it looks in the picture like that's the case. The tangent line there is flat. But we should explicitly show this, and we should show this, we want to show f prime of c equals 0. To do this, we're actually going to cite the result that you all looked at as part of Monday's preliminary work. Right, so Monday's preliminary work asked you to look at this theorem. Let me see, it was lemma 10.6. Right, so lemma 10.6 is the key here. So by lemma 10.6, if f prime of c does not equal 0, well, there are two choices. Then either f prime of c is bigger than 0, or f prime of c is less than 0. And what we showed in that preliminary work is that if f prime of c was actually let's say less than 0, I'll do a sort of a zoom in, right? So here's C, here's F prime, or here's F of C is down here. And if F prime of C was less than 0, then we saw that our function would initially be decreasing a little bit, right? We were able to explicitly find a point over here, point Y, at which F of Y was less than F of C. Right, so if our derivative was initially negative, then I could scooch just a little bit to the right and find a point that was even lower. And that would contradict this idea that F min was actually the minimum value. So again, if F prime of C does not equal 0, then we can find these other points. Well, I should say if F prime of C does not equal 0, then we're in one of these two cases. And in either of these two cases, we can find some nearby point on the function that's just a tiny bit lower. And that will contradict the minimality of that minimum value. So I'm just going to say, dot, 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 contradiction. Okay, how's that sit with everybody? I'm going to take silence to mean that it sits reasonably well. Reasonably well. Okay, good. Okay. A little bit hand wavy right there at the end, I know. But with that, and sort of by referencing the work that you've already done, we're able to knock that out of the park. And it turns out this is actually, I think we're in a place where we have essentially proven the mean value theorem, right? In essence, proving Rolle's theorem is proving the mean value theorem. So now we can finally prove the mean value theorem. This one will actually, I will leave it in a relatively hand-wavy fashion by doing the following. I'm going to say, let F be as described. Consider the function g. So I'm defining a new function g, and g of x is going to be equal to the function f of x minus an appropriate linear function L of x. And to figure out what L of x is, I want to draw a picture. Right, so the image that we had before, here was A. And so here was A, here was B, here's our height f of A, here's our height f of B. Perhaps our function f is just this function. The function L is going to be exactly the linear function that connects these 2 points. Right, so that function there is going to be our L of x. And so we can ask the question, what do we get when we consider f of x minus L of x? Right, well, it's still defined on A and B. But now notice g, so g of x equals f of x minus L of x. Well, L of A, I should say g of A is going to be f of A minus L of A. Those are defined at the same height, and so g of A is actually 0. Right? F of A and L of A are both at this height right here. Similarly, L of B and F of B are both at this height, and so L of B is equal to 0. G of B is equal to 0 because we get f of B minus L of B. So in fact, our function g of x kind of looks like this. It's the difference between the function f and the line L. And so we get this function here. And notice for this particular function, by the way we've constructed it, g of a is equal to g of b. And so we can apply Rolle's theorem. And Rolle's theorem applies here. So at that point, we can apply Rolle's theorem. We can get a result that says that there is some point C, maybe this point, at which g prime of C equals 0. And if g prime of C equals 0, that means that f prime of C equals L prime of C. And that means that our line here is going to be parallel to the line given by L of x. So we've got this is our corresponding C here. So the mean value theorem actually can be derived from Rolle's theorem in this reasonably quick argument, while Rolle's theorem came from a reasonably quick argument from the extreme value theorem. And so I love to talk about all four of these theorems sort of in a row. They start off, sort of like heavy and technical, but then they start falling like dominoes, and we end up proving something really important to the foundations of calculus here with the mean value theorem. Okay, and that about does it for time. So I want to pause there, but are there any questions?
No, it's very hand wavy, but yeah, I get it.
Yeah, definitely a little. So there's still some stuff. I mean, there are some details that we could fill in here as far as like really rigorously showing, I guess, rigorously computing that G itself is differentiable, explicitly calculating what L is, and then explicitly calculating G of A, G of B, and then what G prime equals 0 really means. So yes, there are some things that we could or we probably should compute here. But this sort of gives us the essence or the idea here.
This isn't related to the proof, but are we getting the final today, you said?
Yes, absolutely. So thank you. Yeah, that's what I wanted to end by talking about.
Okay, cool.
Thank you for asking that. Yeah, so the final is written. I was going to email it out to you all, so you can expect it probably in the next 10 minutes or so. The way that it's arranged is similar to the previous midterm. So there's a couple questions that you're allowed to skip, or it gives you some choice in which questions to answer. And yeah, you ultimately have, I was going to make it due midnight on Friday of next week, so you'd have a full week and a little bit. I decided to give you one extra day, though I don't think you'll need it, just because, I'm happy to talk with anybody individually who's in a position due to the pandemic and is struggling to find time. We can absolutely, have a conversation, make something work for you all. But it's of a similar length to our previous test, and you have about a week and a half or so to complete it. So, yeah, that will be going out shortly.
Awesome, thank you.
Yeah, no problem. Got a sleeping cat over here that I'll share with you all. She's been hanging out all class.
She looks
really sweet. Really sweet. Okay, I got nothing else, so I am happy to stick around, talk to you all, and yeah, have an absolutely great rest of your, whatever today is, Wednesday. Have an absolute rest of your Wednesday. I'll catch up with you all, and I will see you all a little bit later. Thanks, everybody.
Bye, Dr. Ross.
All right, bye, Jesse.
Coronavirus!